In this video, I want to continue looking at the definition of the definite integral in terms of signed area. So I basically want to start by looking at some pictures. If I happen to have a function that is like this, y is equal to f of x is up here, and I have x is equal to a here and x is equal to b here, this particular chunk of area is said to be the integral between a and b of f of x dx. And what I want to think about in this particular picture is that the height of any line segment on this area is just equal to f of x, and because f of x is above the x-axis, that height is positive. And the width of this chunk of area, because a is less than b, is the top endpoint of my integral minus the bottom endpoint of my integral. In other words, it's b minus a, and that is also positive. And of course, area is always loosely height times width, and that would mean that this area ought to be positive. So this particular integral is going to be a positive number times another positive number, which ought to be a positive number. Now, if I happen to have the function lying below the x-axis, so if my picture looks like this, so here is where y is equal to f of x lies. And again, I have these two vertical lines. This one is x is equal to a, and this one is x is equal to b. I still have a chunk of area that lives inside here, but this time my height is negative. My height is still equal to f of x, and it is a negative number, and my width is still going to be b minus a, which is going to be positive, and the integral going from a to b of f of x dx is going to be a height times a width, where the height is negative and the width is positive, and of course that would mean that the answer is negative. In other words, just as we had in the previous video, this actually represents negative the area trapped between the x-axis and the curve. So this particular number would be a number that is smaller than 0. And again, this is because the width is positive and the height is negative. So in general, what we've seen is that when the bottom endpoint of my integral is less than the top endpoint of my integral, a definite integral between a and b of f of x dx represents the area that is positive area trapped above the x-axis, and then we are going to subtract off the area that is trapped below the x-axis. And so we know how to interpret this particular kind of notation when we're integrating in the correct direction. Well, what I want to look at now is what happens if we try and integrate in the wrong direction. So what if our lower endpoint is bigger than our upper endpoint? Does this set of symbols still have any meaning? So what I want to do is I kind of want to draw a picture. So here's my x-axis, here's my y-axis, and I'll start off by assuming that y is equal to f of x stays above the x-axis. Now, what I want to notice this time is because a is bigger than b, x is equal to a is over here, and x is equal to b is over here. We still have a nice chunk of area. There's still this nice chunk of area. And I can still think of the height of this area as equal to f of x. So the height is still f of x, and in this particular picture, that would be a positive number. Now, the width is always going to go from the bottom endpoint of the integral towards the top of the integral. And what I want to notice is that the width here is less than 0. The width is still going to be, and let me correct that handwriting, the width is still going to be b minus a, but b minus a in this case is less than 0. So my width is less than 0, my height is bigger than 0, and what that says is that the integral between a and b of f of x dx is still somehow going to be a height times a width, but this time my height is positive and my width is negative, so I'm going to get minus the area that is trapped above the x-axis. And I'm getting minus the area trapped above the x-axis because I'm integrating in the wrong direction. I'm going from x is equal to a over here to x is equal to b over there. Well, I can do this same kind of argument if my function is below the x-axis. So let's look at that. So again, we're still looking at the picture where we've got y is equal to f of x down here, but I'm still going to have a is strictly bigger than b, so I'm going to be integrating from x is equal to a here to x is equal to b over here. And I now have a chunk of area that is trapped here. And we're going to call that piece of area, area A. Well, the integral from a to b of f of x dx has to be somehow related to this white area, but how? Well, what I want to notice is that the height in this particular chunk is going to be f of x, but f of x is negative. And the width, we're still going from x is equal to a to x is equal to b, so my width is going to be b minus a, but because a is bigger than b, my width is now less than 0. And so this definite integral is again going to represent some kind of height multiplied by some kind of width. And the height here is negative, and the width is negative, so the area is going to be a positive area. In other words, in this particular scenario, my integral is going to represent positive the area under the x-axis. So what this means is that we have the following basic kind of relationship. If we are integrating in the correct direction, in other words, a is less than b, then our integral of f of x dx is going to be the area above the x-axis, subtract off the area below the x-axis. But if we integrate in the wrong direction, we want to have a bigger than b, then the integral between a and b of f of x dx has a negative width, and this will wind up being minus the area above the x-axis, add back the area below the x-axis. And in the next video, we'll look at a specific example.